So in this section, we're going to talk about cylinders and quadratic surfaces. And this is a lot of fun. This is where the three-dimensional stuff begins to get a little bit more interesting. And so I want to begin just talking about the word cylinder. So I want you to picture what you think of when you think of the word cylinder. And typically, we think of cylinders as round, like a round tube. But we're going to call any surface that's a stretch of a 2D graph a cylinder. And I'll just show you what I mean by examples. If you want to get a little bit more precise, I would encourage you to read the book. But for example, we can think about drawing a circle in 2 space, and then you stretch it, and you get the classic cylinder. We could think about drawing maybe a parabola in 2 space, and then stretching it, and you get this trough-looking thing. We'll put a line on the bottom as well. But we're going to call both of those cylinders because you're taking a 2-dimensional shape and then stretching it. All right, so let's actually work out some examples of the kind of things you're going to see and you're going to need to be able to figure out. And so what I want you to realize is that cylinders, or what we'll think of in some ways as stretch graphs, there's a missing variable. And so when you look at this one, you see z equals x squared. And so it's helpful if you graph it in the zx plane. So I'm going to think about the x-axis as the usual x-axis, but instead of a y-axis, I'll have a z-axis. And you should instantly recognize this is a parabola. There's the standard x squared parabola opening up. Okay, the key is that you stretch this graph. When you want to graph it in 3 space, it's not just a parabola. You want to stretch this graph along the missing axis. And so we're going to go ahead and take this picture that we drew. This is living in the ZX plane. Here's again a copy of the ZX plane, and we're going to graph it there. So we're going to graph a copy. Now it's been kind of flipped. This is the negative x-axis over here, which is over there. So you sort of got to rotate this thing over and then slide it over. But you put it there, and then it doesn't matter what y value you pick. You can pick y equals 0 and you're in the zx plane, or you could pick y equals 5 and z is still x squared. And so you just take, another copy of this parabola in a parallel plane, and that's what you get. So this trough actually extends on forever. We've just graphed a piece of it, but you sort of get the idea. And if you want to be fancy, we can sort of color it in here a little bit. And I'll try to do that for it, at least this side. I could obsess over this and waste a lot of time, so I'll stop. But the big takeaway, I guess 2 big takeaways. One is that this is called a parabolic cylinder. All right, and I'd like you to know some of these basic names. Second big takeaway is that you stretch this graph along the missing axis. And in this case, sorry, not axis, the missing variable. We'll say the missing variable axis. And in this case, that's the y-axis, because looking back at your equation, there's no y's there. And so you sort of know whatever the graph is in the xz plane, you're going to stretch it along the y-axis. Okay, so similar example. We're given this equation. Now we're thinking in terms of 3 space, not 2 space. If I ask you to graph this in 2 space, you should all instantly recognize that that's just the unit circle. No problem. So what do? You notice the z variable is what's missing. Z is missing. There's no z's here. So I'm going to graph this picture. This is, by the way, the x-axis and the y-axis. So I'm going to graph this picture in the xy plane. So here's x, here's y, here's z. And this is going to be a little bit tricky, but something like that maybe. And then we're just going to stretch it along the missing axis, which is the z-axis. And so we get something that looks like that. And my cylinder isn't perfect, but it sort of works. It looks like the bottom is a little bit bigger than the top. It's supposed to be the same, but I'll blame the iPad. So this is what you could, if you wanted to name this, you could call this a circular cylinder. And of course, we stretched along the missing variable axis, which in this case was the z-axis. All right, so I wanted to just do a quick review of the formula for an ellipse. Now, I've written the formula down when the center is at 0, 0. Everything holds. If you want to shift this thing, you just write it as x minus h squared plus y minus k squared equals 1 divided by a squared over b squared. This version would just give you a shift. It would put your center at h comma k. But let's think about it when it's centered at 0. If the number here, a, is actually bigger than b, you stretch along the x-axis. So it's going to be longer this way. Whereas if b is the bigger number, then you stretch along the y-axis longer that way. And you can talk about the foci and all of these things, but for our purposes, if we can just figure out sort of the 4 distances here off of the center and graph an ellipse like that, then we're going to be good to go. That's plenty accurate for us. So here's the third example that I want to do with you. You're given this equation, and you notice that there's no x variables, and that's the big clue that this is going to be some sort of a cylinder. It's going to be, I'm going to go ahead and guess that it's going to be an elliptical cylinder, but let's see how we can figure it out. So I want to put this in standard form, which means I need to complete the square. So I'm going to go ahead and factor, I'm going to group the y's and the z's, and I'm going to factor out what I can. So I'm going to have a 4y squared minus 4y, I'm going to leave a space, plus 9 times z squared minus 2z, leave a space, equals 11. Okay, so now I want to take half the middle term. Half of negative 4 is negative 2. Square it, add it, you get a plus 4. Half of negative 2 is negative 1. Square it is 1. Add it, you get a 1. I really added 16 to this side, so I've got to put a plus 16 over here. And I really added 9 to this side, so I've got to put a plus 9 over there. And now I get a 4 times y minus 2 squared plus 9 times z minus 1 squared equals, what do we get? 25 and 11 is 36. I want to get this thing equal to 1, so I get a y minus 2 squared over 9 plus z minus 1 squared over 4 equals 1. And now in that standard form, you can sort of see that the center of this thing is what? 2, 1. I'm working, by the way, in the YZ plane. So we can even sketch this if we want. Y-axis, Z-axis, we're going to center this at 2 and then 1, so right there. And then how do you graph this? Well, you take the square root of this number. Whoops, let me use my highlighter here. So in the y-axis, I'm going to go 3 in both directions from the center. So 1, 2, 3, and I'll put a point, and then I'm going to go 1, 2, 3, and I'm going to put a point. Whoops, I'm not sure. I clicked on the wrong thing, I think. There we go. 1, 2, 3, there. There we go. And then in the z-axis direction, off the center, I'm going to go square root of 4, which is 2. So I'm going to go up 2 and then down 2. And so I get something that looks like this. Now that's not a very nice cylinder actually at all, but it looks more like a circle the way that I've drawn it. Let me try again. I was kind of dreading trying to do this section on the iPad because it's sort of hard to draw these things. All right, that's good enough. So I want to sketch this in 3 space now, right? That's the goal. We're viewing this equation not as a 2-dimensional equation, but as a 3-dimensional equation. I graph it in 2 space first because I see there's a missing variable, so I know I'm going to stretch this graph along the x-axis. And so now, actually, I've gone ahead and graphed it ahead of time and just so I could copy it and paste it to save time. So there, this cylinder here doesn't look exactly the same as this cylinder. It is supposed to be the same. I kind of stretched it out a little bit more. And then you stretch it along the x-axis. I should label my axis. This is the x-axis, the y-axis, and the z-axis. And so that's it. So that's cylinders. I guess we could name this. We could say that this is an elliptical cylinder. All right, so let's stop here. And I would just commend you to thumb through your book quickly, and you can look at the way they present the material a little bit differently. They focus on rulings and a few other things, but this is the same basic notions. And this is what we're going to need for this class, what I'm showing you here. But do have a look at your book as well.